Welcome to the AP Physics lecture. Here I'm going to be covering dynamics, which is on an incline. Normally we're going to be talking about the normal force and the acceleration. So this is very crucial because a lot of problems in this section deal with an object sliding down a ramp. So when an object is positioned on an incline, its motion along the incline will always be at an angle to the traditional coordinate axis system. Normally, we have our x as something left to right, right? This is normally our x-axis. Then what we go up would be our y-axis. This is what I mean by the traditional coordinate grid. But when it is positioned, a block is on a surface, on a ramp surface, we normally position it so that the axis is now on the block to make the math much easier. So here we see this as the y-axis. Then we see down the ramp or perpendicular to the ramp as the x-axis. That's why they say, since an object on the incline moves parallel to the incline, simply tilt the axes along the x-axis parallel to the incline. So you see how this is parallel to the incline? So this is parallel to this. Okay? I'm going to clean this up for you and label it again. So this is your x-axis. So, sorry, this is your y-axis, and this is your x-axis. Okay. Forces acting on the incline. We know that the orientation makes solving motion along the incline easy because force of gravity is always directly downwards to the center of Earth. This is perfectly true. But here, when we tilt it, the force of gravity becomes like a diagonal. So we have to break it down. It's broken down into its x and y component. Please understand that there is now a horizontal and a vertical part, a cosine and a sine part. Remember, the forces at an angle to the coordinate system must always be split into its component form, the x and the y component. This is theta. Okay, this is the angle in of itself because this comes from alternate interior angles. The right triangle formed by the component are similar triangles to the incline itself, and the angles of the incline can be used to determine the magnitude of each component. If this is FG sine theta, you will see that the parallel to the surface here would be FG sine theta. So you could also draw it like right here if you would like. If theta is here, this would be FG sine theta. Sine is going to be our opposite. Okay? That's FG sine theta. Then the one that goes down is the cosine part because it is adjacent. So it's FG cosine theta as well. Please understand here that the x component of the force of gravity is Fg sine theta. So this is the x component of gravity. And this influences the object's motion along the incline. This is what's causing the object to slide. Fg sine theta is always present on an incline. Always present. It doesn't disappear. When the summation forces along the incline, Fg sine theta is used in place of Fg and always must be included. The y component of the force of gravity presses the object into the incline. So the Fg cosine theta, the blue arrow, is what is keeping the object on the ramp. The fact that the Fg cosine theta is pressing on the ramp surface, the surface is going to push back. When an object pushes against a surface, the surface pushes back with a normal force. That is that blue line. So here the normal force becomes Fg cosine theta. the normal force is equal to the component of the force of gravity that is perpendicular to the incline. So the incline diagram can simply be broken down like this. This diagram explains the geometry of the force and their components that act upon an object's positioning on an incline. The free body diagram that you need to be able to draw would look like this. Force of gravity is always down towards the center of Earth, and the normal force here is tilted weird because why? The force, because it is the opposite to the FG cosine theta. The alternate design looks like this, where you see what the FG sine theta is what's pushing it down. The FG cosine theta is pushing it on the surface, and the normal force is FG cosine theta. Okay, you need to be able to draw the free body diagram on the AP exam, but you also have to understand the alternate design to solve the problem. Here's example 3. Here's the problem. A 10 kilogram mass on a horizontal surface is pulled by a 40 Newton force at an angle of 30 degrees. Part 1, find the acceleration of the block. And part B, find the normal force exerted by the table on the block. So we look at the problem first. We saw that it is parallel to the incline. So the motion is only in the x direction. So I said the summation of the forces in the x direction is equal to ma. Then we saw that it is stationary in the y direction. So summation of the y equals to 0. The object isn't floating up away from the surface. Here's the free body diagram looks like. And if you would like to see the component form, it looks like this. Okay, Tx is just the horizontal part of the tension force, and Ty is the vertical tension force. Let's do the summation of my forces. The summation of my x forces in my x direction is just your T cosine theta. That comes from Tx is equal to T cosine theta, and that's your only x part. Your y is your Ty here, which is equal to T sine theta, as well as the normal force going up, subtract by the weight going down. So let's solve for acceleration. So this, we said that summation of my f equals to ma, so you plug it in here. So ma is equal to T cosine theta. Divide by m to both sides, you get a. So a equals to 40 times cosine, divide by 10. So that is the acceleration. It's roughly 3.46 meters per second squared. Now to solve for the normal force, we use the summation of the y forces. Solving for n, but here we set it equal to 0. Why do we set it equal to 0? Because here it says it right here. It's stationary in the y direction. That is the reason why it equals to 0. You add w to the other side, and then so you add w to the other side to solve for n, then you subtract t sine theta to the other side. Okay. Now you can plug it in. W is just mg, understand that, t and sine theta. So we know m is 10, gravity 10, T is 40, sine of 30 degrees. Okay, so N equals to 78 newtons. Good. Let's look at example 4. This is now a 40 kilogram block, but now it's sliding down the ramp. Remember, you have to break, the force of gravity is broken up into its horizontal and vertical part here. Right, so let's look at the problem and see where the motions are. We see that in the x direction, it's parallel to the incline. It's accelerating. So summation of my forces in my x direction is equal to ma. But we saw that the object is not floating up or going straight down into the ground. So we say it's stationary. Summation of my forces in my y direction equals to 0. The free body diagram looks like this because there are only two forces here, the normal force and the force of gravity. It's frictionless. There's no friction here. It says frictionless. Right here, frictionless. If you break this down into its component form, we see that the let me change this. Let me change the color of the pen so you can see this much better. Okay, so we look at the vertical part component of force of gravity, which is going to be Fg cosine theta. And then we have the horizontal part, which is going to be down here, Fg sine theta, because again, theta is right here. Okay. This is the free body diagram. Don't draw the component. So this is what I was trying to get you to understand. Okay. So Fg cosine theta is in the, remember this is the y-axis and this is your x-axis. Okay. So we do the summation of my forces. In the x direction, it's only Fg sine theta, and in the y direction, the summation of the forces is just n minus Fg cosine theta. Now we could solve for it. Fx is equal to ma. That's what we said here because it's accelerating. So ma is equal to Fg sine theta. The masses cancel out. A is equal to g times sine theta. A is equal to 4.9 meters per second squared. Here we saw that it is stationary in the y-axis, so this goes to 0. Plug in everything else. Fg becomes force of gravity becomes mg. Add mg to both sides. Mg cosine theta to both sides. Okay, then plug it in. You get the normal force equals to 42.4 newtons. Those are your two common problems that you see on the AP exam. I'm going to give you the 4 possibilities that you're going to see when it comes to the normal force. You're going to see the normal force equals to mg when it is on a horizontal surface. Then you are going to have mg, but this time there's a tension force pulling it up. So it's going to be minus mg. This comes from the person pulling up. Now, it's pulling up, but it's at an angle. Do you see this? This is pulling up because there's a sine part here, pulling up at an angle, Then lastly, when the normal force is just mg, that means it's down a ramp. Okay? These are your four common examples that you're ever going to see the normal force. Nothing more